Hello everyone. In 3D computer graphics rendering, one of the most frequent stumbling blocks for newcomers is the process of perspective projection. In this video, I would like to shed some new light on the matter by illuminating it from a different vantage point. It is my hope that this new way of looking at it would provide some much needed clarity and insight into what's really going on there geometrically, as opposed to purely computationally. One major reason for why this topic is so often confusing is that while conceptually the problem looks like a projection of three-dimensional space onto a two-dimensional plane, it turns out that something very different actually happens when using graphics hardware, where three-dimensional space actually stays three-dimensional, but ends up being warped non-linearly such that a specified trapezoidal volume gets fitted into the shape of a box. This mind-bending concept of warping 3D space itself while keeping it three-dimensional is where much of the confusion starts. Turns out that it's a composite of two kinds of transformations. The first part is a purely linear transformation in four-dimensional Euclidean space using a standard Cartesian coordinate system. The second part is a non-linear transformation in 3D projective space using a four-dimensional projective coordinate system. One other reason this topic gets confused, at least for some people, is the way it's being explained, where the prime focus is on the mathematical or computational aspect, and much less so on the geometric intuition. And understandably so, as much of the process actually involves four-dimensional transformations, and part of it is in a non-Euclidean projective space. That can make it pretty challenging to visualize geometrically. As a consequence though, the math involved gets a bit murky at times, where a transformation using a matrix appears like a hack or even an abuse of linear algebra machinery, without getting a clear picture of what happens in this transformation geometrically. And while it is possible to eventually get it all right algebraically and in code, I find it deeply dissatisfying not to be able to conceptualize what's really going on there. And so in this video, I would like to go deeper into it and try to make some better sense of things, taking a different approach to the one typically taken, with the hope that viewers come out of it with a deep intuition and insight into this confusing space. It's the kind of video I wish I had access to when I first started learning computer graphics rendering and spent a long time struggling with and scratching my head on this very topic. The main key observation for perspective is that things appear to grow as they get closer to us and shrink as they go farther back away from us. The objects don't actually change size, they just appear differently based on how far away they are. When rendering 3D objects into 2D images using computer graphics, we want to replicate this effect. Computer graphics, the surfaces of 3D objects is typically represented as being made out of flat triangles. Each triangle has three corners at different positions in 3D space, so they are represented in a computer as a 3D vector. Projecting a 3D object in computer into 2D effectively amounts to projecting all of its triangles by transforming the 3D vectors that represent their corners. So we're looking for some vector transformation that would take all the corners from where they are in 3D space into where they'd need to land on some 2D plane situated somewhere in that same 3D space. And we want the 2D size of the projected image of the 3D object on the plane to be inversely proportional to how far away it is from where we're looking at it from. However, something gets lost when we do that. The space that we end up is two-dimensional, so it lacks any notion of depth for each of the projected triangle corners. And that's a major problem for rendering because we need that depth information to determine which object surfaces are closer to us, so we render them as occluding further away ones. For this purpose, and possibly others, this is not actually what the hardware graphics does. It retains the depth information in what's called a depth buffer. But to do that, this simple planar projection we did is not going to be enough. we need to have the 2D space we end up with after projection to still contain depth information. In other words, we actually need to still be a 3D space, but one in which its 2D space behaves like the 2D space of our simple projection plane in terms of what depth-based proportionality is scaling. So we need to decide what portion of that 3D space to fit within those finite bounds. In other words, we need to somehow bound the 3D space correspondingly to the 2D bounds of the image and define exactly what that correspondence looks like. Alright, let's start analyzing this process step by step. So first of all, we start with our view space, which means that everything is in terms of where we're looking at, or in terms of our viewpoint. So this is the origin of our coordinate system. We're using a left-handed coordinate system with y pointing up. So everything is already in this space in relation to where we're looking at, and our forward direction is positive z-axis. Okay, now this box right here is where all of the space that we want to be participating in our final image is going to land in before we do the rest of the rendering procedure. Now this box is a cuboid, is like a half cube, and that's actually a convention, and there are different conventions. There is a convention with a full cube, and it is a kind of a normalized cube. So this cube, this convention is used by OpenGL and Vulkan, I think. It's just a convention for how to define this space where everything is projected into. So this box extends from -1 to 1 in all three axes, and if we go with the OpenGL one, the Direct3D one, it's going to go from 0 to 1 in Z and -1 to 1 in all the other axes. Okay, so now whatever's going to fit in here is going to be defined by this trapezoidal thing right here that we're going to spend a bit of time talking about. So we're going to parameterize this shape with a few measures that end up determining how the perspective projection is going to put all of what's within it in this box. It's basically our way of telling the perspective projection process what are the bounds of the space that we're interested in projecting. Alright, let's start talking about how to parameterize this view frustum, this cuboid shape. So we're going to use a conceptual aid with this configuration right here, with another auxiliary plane that's separate from the near and far clipping plane, and we're going to define such that the shape of the view frustum always wraps around it. And as you can see, it's completely independent of the near clipping plane or the far clipping plane. Those change independently of that. They control the far and near extents of the space that we're capturing, and this other plane controls just the shape. So what can we see about this plane? Well, if we keep its dimension fixed and just push it forward and backwards, that controls the span of this trapezoid. And the way that's done is through this ratio within this triangle. The ratio of this distance over the half of the height. And we have set the half of the height to be 1. So this ratio of distance over this is just going to be the distance, as we can see right here. Now, usually you will see this represented as a field of view angle. The full angle is going to be twice this one, but you take this one and you typically see what in literature you use a cotangent or 1 over the tangent. This is just an indirect way at getting at this ratio, because this ratio controls the slope of this line, and it controls, that way it controls the span of this view frustum, at least this span. Now the other measure, we're gonna set it to be the aspect ratio of the final image. So the aspect ratio is again a ratio, so it's not about resolution of the image, it's more about the relationship between the width and the height of the image. We're going to set this to be the aspect ratio because, as you can see, this over 1, which is thus just this, is equivalent to the width versus the height of this plane that we've situated here, using this principle of triangle similarity, because this triangle is a smaller version of this one. Okay, why is that useful? Well, as it turns out, for our next kind of stuff that we're going to talk about, we will actually need to transform this space right here first into a space where we if we had a view frustum that is actually like a perfect pyramid that goes like 90 degrees right here and right here. So it extends fully diagonally in X and Y. And we'll see a bit later why we need that, but that's the first step that we're gonna have to deal with. And let's see how we do that. So our first transformation is just gonna look like this, which is just stretching the space in X and Y such that our trapezoid fits within this perfect pyramid along X and along Y. So how do we know exactly by how much to stretch this space? So one observation we can make, because this pyramid is a diagonal pyramid, then every point along this line is extending upward by exact amount that it extends forward, and the amount by it extends forward is just L. That's what we've defined. So we can see that the amount by which we need to stretch things up is just this measure L over what it's currently at, which is 1. So it's just L. Similarly, what we have here is the same story. We have a diagonal line which extends to the right by the exact same amount that it extends forward. And we already know how much it extends forward because that's L. So we need to extend it by L over however long is this thing, which is A. That's what we've defined. And as we remember, A is just, it's representative of the aspect ratio of the final image. So we have this L over A for a transformation here, and just L for a transformation for along the y-axis. So it looks like this. So we can already see some relationship between what happens to the space with its transformation and the parameters that we have set our auxiliary plane here to be. So say we had a wider image. So we had a longer aspect ratio. Well, to fit it within a square, we need to squish it a bit inward. So our image becomes like this. Don't worry, by the time it gets rendered, it'll be scaled up back again. But for the purpose of putting it in the cuboid, we're gonna want it to be square-like, so we're stretching it in. Similarly, if we have an aspect ratio smaller than 1, then we'll be stretching it wider. What about the focal length? Well, as you can see, if we pull it inward or pull it back, it ends up scaling everything up if we go in. This is the effect of zooming in like in a camera. That's what ends up happening because we're capturing a smaller portion. As you can see, you're capturing a smaller portion of space that ends up needing to fit in the same square. So it ends up getting stretched upwards or outwards. Now, going forward in this video, I'm going to use this heads-up display that I've situated here. It's just going to show the parameters that we're using right here. And we're going to stack up left to right row major matrices as we do the transformations that we need to do step by step. So P prime is going to be the result of the resulting vector after all the transformations, and we're going to right multiply it by a bunch of row major matrices. So we're just going to use this to keep track of what are the matrices that represent each of the steps of the transformations that we're going to use. Now ultimately we're going to collapse all those or coalesce those into a single final matrix, but for the purposes of learning how all of this works, I found it a lot more intuitive to keep the steps of the transformation separate and visualize each one. So the next part is going to be a bit more tricky to explain because we're going up to 4 dimensions, which is obviously impossible to visualize. So what we're going to do, our strategy, is going to be that we're going to slice our view of space. So we're not slicing space itself, we're just slicing our view of it, the same way that we can slice a view just by looking from the top. We lose all information on these planes here if we're looking at them from the top. So this is what we're essentially doing to 3D space, so that we're only considering what happens to X and Z. This way we end up having the up vector, the up direction available for us to represent the 4th dimension, and we're going to call this axis W now. So this is the same 3D space, we're just looking at a kind of a 2D slice of it, and we're going to do the rest of the transformation here to show what is happening in the 4th dimension, which will be represented here by the up direction here with this W basis vector. Similarly, you can see in the matrix, I've dimmed down the Y dimensions of the matrix. So we're really dealing, it's as if we were dealing with the 3x3 matrix, with the second column and row kind of being ignored for now. This will allow us to visualize what's going on in the ZXW 3-dimensional space, which is the 3-dimensional subspace of XYZW, the full 4-dimensional space where the transformation occurs. So I hope that's clear. So now first we'll need to talk about what is the nature of this 4-dimensional space, which is a projective space. It's non-Euclidean. What does that actually mean? So I'm going to just hide this geometry for now. We'll get back to it a bit later. Just to show what I mean by projective space. Projective space is represented by these lines through the origin. That's what it actually is all about. All the lines that go through the origin. Now, if we consider the lines to be the actual unique elements of this space, then you can see that any point along a line, if we've chosen arbitrarily this line right here that goes through the origin, any point along this line we consider to be the same, we consider to be equivalent. Another word for saying is we can say it's homogeneous. Homogeneity means sameness, or like same shape, or equivalency. That's what the term homogeneous coordinates come from. It's another word for projective coordinates. It's just a synonym. Okay, so we can see that we have these lines through the origin, and what more, we're going to consider this additional plane that's situated exactly one up above the regular plane in the W direction. We'll call this the reference plane, and it's kind of special because, as you can tell just by looking at it, that each line that goes through the origin crosses this plane in a particular point, like this. Now, I said all lines, it's almost all lines, because there's all the lines that are flat on the original plane of our space here, which is with the W of 0. And those lines are called projective points at infinity. We won't go into that, don't worry, we don't need it for now. So we're going to consider all the coordinates that are non-zero along the W axis. And all of those, represented as these lines through the origin that are not flat on the ground, they will all cross this reference plane at a particular point. And that's useful. And we'll see a bit why. Because then we can say that every such line, every such point that lies on any such line, we can always bring it back to this reference plane by just scaling it down such that its W coordinates becomes 1, because that's where it would be on this reference plane at W of 1. So you can call it a normalization, but actually the term normalization, if we scale it by the length of the original vector, will end up at the sphere at the center of the world, which is not what we want. We want it to land on this plane at a height of exactly 1. So we divide all of the coordinates of the original point where it started by the original W, the height where it started, such that it's still aiming at the same direction. It's just a bit shorter, and it meets this reference plane at W equals 1. Now, I said we're looking at a slice of a 4-dimensional space, a 3D slice. Another way of thinking about it is we're having the whole of 3D space situated within 4D space. Well, 3D space doesn't have a 4th dimension by its own, so we can slot that 3D space wherever we want along this extra dimension. So we're going to choose to slice it on this reference plane. So all our coordinates, it's not a transformation, it's just when we add the the additional dimension, the different additional coordinate component to all our vectors, we're going to set it to a W of 1, which means geometrically that we're slotting it in on this reference plane as a starting point. Now already you can look and see we have our bounds of our view frustum here on diagonal lines, and that's going to be very useful very shortly. Now, as you can see, the slice of our target cuboid here is just this rectangle, and as we just said, in projective space what we actually care is lines through the origin. So these are the lines through the origin that represent projectively this this rectangle. So what we really after is taking this shape, this trapeze shape, and sending it here into this rectangle. So we're going to focus on this particular transformation now of taking this trapezoid into this rectangle. So we're really talking about transforming these 4 points, corners of this shape, into these other 4 points. Now remember, we're in a projective space, so the target points that we're aiming at are actually these lines through the origin. So really what we're looking for is to project these 4 corners of our trapezoid to somewhere along the lines that we're talking about, respectively for each point. Because as you can see, this forms some wobbly shape here in 4 dimension, but wherever that shape, whatever shape that that rectangle ends up, or quadrangle ends up taking, we can always just drop it down back to the reference plane, which will land us at exactly our rectangle that we want. So let me show this again. So we're letting this the target of where we want to land in on those lines wobble wherever they want to be, just as long as they are on that particular lines through the origin. These are the particular projective points that we're interested, and we just end up with this shape, and then we can just drop it down always to back here. Now, where exactly where we land on these 4 lines is kind of arbitrary, so it means we can choose something that's convenient for us to compute and conceptualize. And you can already see that there's a lot of diagonality here, both in the target and the source where we start from. And that's exactly why we put all this work up until now, to make our trapezoid into this perfect pyramid-like shape. Because now we have a lot of diagonality we can leverage in the further computation. So we're gonna pick some points that are very convenient for us, which would be these points. Now I'm drawing, we're gonna focus on the right side, because the left side is gonna be the same, it's just a mirror image of it. In terms of the transformation, our transformation are going to be just in the Z and W axis. We're not going to do anything about X anymore. We've already done all we need for that. So we can just focus on the right side with these 2 points. So our transformation brought it to here actually. So as you can see, because of this diagonality, the amount by which we need to go up, if we were to start from 0, the amount by which we need to go up is exactly the amount by which we are in forward direction, exactly as we saw before. So it's the same exact story again. And it's the same for this one, because this is a diagonal line. So the amount by which we go right is the exact amount by which we go forward for this one. And for this line, for the back point, it's the same, only in the W direction. So we're looking for a transformation that takes this point up and then back by the same amount that it is in forward. So this is actually the near clipping plane, so we know how far away it, because we have set it already, right? It's this one right here. And the far clipping plane, we want it to go up by exactly how far away it is in z, which is just f. That's the far distance that we've already set. So we want this corner to go up here and this corner to go up here. So it's going up by different amount, but the exact same amount that we do in z. So we're looking transformation for transformation that does exactly that, and that's called a shear. So what we're going to do, and I'm going to grab this W axis and bring it down temporarily just to illustrate. If we now take the Z axis and lift it up by 1 in the W direction, look at what we have done to our space. We have just lifted up, it's not a translation, it's just a shear of Z in the W direction. Okay? That's what we're looking at here. So that brings our point here to here, but ultimately we want it to go over here. So we need to shift our space to the left. But look, we already have the far points exactly where we want them. So we're looking for a transformation that takes these 2 points at the near end back to 0 by n, but leaves these 2 points exactly where they are. So we're going to do it in 2 parts. First of all, just bring those 2 back, and that's a translation. But what is a translation? If we have a look at our space flat on the ground, if we take the W axis and we shear that to the left, that is exactly what a translation is. It's a shear in 1 dimension up. So it takes the entirety of the subspace here and just moves it as it is to the left, like so. So that's how we go left. And now if we combine these 2, then we see that we end up, I didn't do it exactly, so I'm gonna cancel this manual thing and just show you. So this is the first part of just taking it over here. But look, we've lost these points. They're now farther closer than where we need them to be. But because our 2 points are at 0 now, at 0 in Z, then all left for us to do is to scale it up by a little bit to bring those 2 points back over here. And let's see how that looks from the top. I'm going to hide the geometry so we can see. So looking at it from the top, we want these 2 points to be over here. So we want to stretch up by Z by some amount that leaves these 2 points because they're at Z of 0, but we're stretching these points up to here. And how much is that? Well, this right here, how much we're currently at, is Z, the original one, minus n, because we've moved n back. So it's f minus n. And we want to bring it back to f, which is on the diagonal, as we saw. F goes here and here. So we want it to be f. So we just need to scale up by however much f is relation to this measure, which is f minus n. So we need to stretch by f over f minus n. So let's apply this transformation. It goes like this. Alright, play it again. We're going here, and we're stretching z by exactly f over f minus n. And there we have it. We have all 4 points on the projective lines that would send them back to here. So let's see that. As you can see, they go all the way down, and we know how to do this. It's just dividing by w for each of them, right, as we saw before. So this gets divided by w, which is f, goes back to here, and this gets divided by its own w, which is n, goes over here. And there you have it. So having a look at how this looks like, will look like the transformation like this. Now, as I said in the beginning, we don't always want to deal with a rectangle. We sometimes deal with a cube. So how would that look like? So let's go back a few steps. First, though, notice that we can view the final matrix, which looks like this. If you just multiply it out, just mechanically, you'll end up with this transformation matrix, which is the transformation matrix for the projection matrix for direct 3D. You can look that up. That's exactly what we ended up with here. I'll note that it's not actually a projection matrix. All projection matrices that are called projection matrices are not actually projection matrices. They are linear transformation matrices that put the space in this configuration with a bunch of shears and translates and scales. That's all we've done. That's all you can do with matrices. You can't do nonlinear transformation. But you can bring the space into the particular position like this, whereby you can then do the homogeneous normalization that we talked about, which is the actual projection. It looks like this, right? It's a separate step. That's the separate step, that separate nonlinear step that happens by the graphics hardware. We don't do that in code ourselves, unless we're writing a software thing. Okay, so let's back up and get back to the cube story. So we start off with the same story. All the stuff that we did around in X and Y is exactly the same. But instead of having this rectangle, we actually have a square. And look, there's the same kind of story of diagonality involved, where, you know, all those lines are diagonal, so we can leverage that as well in here. And we have the same story. We want to squish this whole space all the way into this square this time. Okay, so we play out the same scenario. So we want to have these lines. We want to go from these points onto these lines. And it doesn't really matter where we go on them, because once we do, doesn't matter what shape we end up in, we can always just drop back in the same way. These are lines through the origins. They behave projectively in the exact same way. So, what are the transformations that we need in this case? So first of all, that's the X and Y. We just redid it again. Now we need to go up like we did before, but this time we need to go a little bit more forward. it looks like this. So we did this step of going up and to the left, okay? But now these 2 points need to go back here as before, but these 2 points have to actually move forward. So how do we do that? Well, so the first thing we're going to want to do is just move ourselves forward so we can take these points over here. So it's just another one of these shears. However, now we're shearing at the level of W. This takes further away points at a kind of faster speed than the lower points. But if we have a look at how this looks now from the top, if we want to take this back to here, we actually need to scale up by f plus n over f minus n, because we have f plus n here and f minus n here. But there's a problem, because we can't actually do that. If we try to actually do that, we get this, which is not correct, because we're moving further back, because we're scaling z from a point that we already have here. So that doesn't work. So let's go back a bit and try something else. Remember how shear works by taking things by the amount by which they are further from the axis in which we're shearing. So going this takes us back by exactly f for these 2 points at the top. We can see that takes us by exactly f back. So what we can do instead is, if we go back to here, to this position, before we go backwards, we're going to stretch it, because in here we're kind of an opportune point where the n, the near clipping plane, is at 0. So we're free to stretch things, changing just the far without changing the z. So we're going to capitalize on that, and we're going to stretch up instead of by what we did before. We're going to do a bit differently. So instead, as we'll see, what we'll do is going to stretch it a bit more. So we're taking another f backwards, because we know that the next thing we're going to do, this shearing, is going to take us 1 f back. So we're going to preemptively account for that and scale it by another f, which looks like this, taking us back here. And now if we do the shear, now we're taking us, this is just by 1 unit shear along the W, which takes our near place back by however much it is in W, which is n, landing us here exactly where we want. And we're taking the far, now that we've overstretched it by an additional f, when we take it back, we're landing exactly where we want. So now all our points, all our corners of our space here are exactly on the diagonal lines go through the origin, which are the projective points of our square here. And because of that, if we now normalize everything projectively, we can see that our space lands exactly within the square that we're looking at as our target. Now, there's one little thing I want to add up. So first of all, this is how our final matrix looks like for OpenGL, with one bit of difference. What you'll see when you search on the internet is this entire third row gets flipped, gets a minus sign. So the minus sign here and minus sign here. So it looks like this. So I wanted to quickly show why that is and what it looks like. So we end up another matrix that just does this flipping of the Z axis. What this ends up looking projectively, and this last visualization is not particularly accurate, but just for illustration, is something like this, where you see the things get flipped around back to front. So we're not looking at it from this side, and that's it. That's the matrix that the formulation of the matrix that you'll tend to see on the internet. For the other two axes, x and y, you'll probably see something with alphas and 1 over tangent or cotangent, and we already discussed what that means. But that's it. I hope you enjoyed this video, and big thanks to 3 Blue 1 Brown for making this context and pushing me to making this video, which I wanted to make for a long time. So I hope you enjoyed this video. Just if you're interested, the software that was used to do the visualization is based on my software project that I wrote from scratch. It's a software renderer written in C. So if you want to have a look, I will also include this entire presentation with all the interactive aspects of it, so you can play around with it yourself.